Let us quickly recapitulate as to what we had done in the last class. In the last class, we started with atomic theory, right? These were the topics that we had started up with in the last class. What did we have? We had the Dalton's atomic theory. First of all, that was like the simplest atomic theory where the concept of an atom actually came up, right? And he stated that atom is just indivisible. That was one of the facts that he had talked about. Then after that, it took some time for the development of the subatomic particles and the microscopic entities, which came through a number of experiments that we had discussed last time. What was one of them? Cathode ray experiments actually paved the way for the discovery of the electron, right? Electron, that was the negatively charged microscopic particle within your atom. What is an electron? It's a microscopic particle only. And then the discovery of electron was done basically by whom? The name of the scientist comes in the MCQs at times. J.J. Thomson. Then the charge of the electron, E by M ratio and M ratio had come by a series of experiments which were done, and you should be remembering these values at least for your entrance examinations. So you know that charge is equal to 1.6 into 10 power minus 19 coulombs, and you have your E by M ratio as 1.758 into 10 to the power 11 coulombs per kilograms, and you have mass of the electron as 9.1 into 10 to the power minus 31 kilograms. Similarly, then as science was progressing, there was discovery of the protons, which was another positive microscopic particle which existed within your atom, but it was like not spread throughout, it was concentrated only in a particular region. So there we talked about the protons. The charge in the proton is equal and opposite to that of the charge of an electron. This all of you all know. And because atoms are electrically neutral, this is something that you've done in smaller grades. Because atoms are electrically neutral, so you know that the number of electrons are always equal to the number of protons in a particular atom. Then you have the mass of the proton, which also needs to be known. You know that proton is a little heavier than your electron. Electron is the lightest microscopic entity that we are talking about as of now. So you have mass of the proton, that was 1.6735 into 10 power minus 27 kilograms. And then there was discovery of neutron, and I hope you remember that neutron was discovered by Chadwick. Neutron was discovered by Chadwick, and the charge on the neutron is neutral. And when you talk about neutrons, this is something that we didn't talk of, because I presume that you know neutrons and your protons together are known as nucleons, right? And when you write down the atom in totality, how do you write down? You write down the atomic number as a subscript below, then you have your element, and on the top you write down the atomic mass. And then we discussed the concepts of isotopes, isobars also in the last time's class. Then we had the development of the model that came from the Thomson in the first go, because the atomic structure was what was to be actually unfolded. So what we had was Thomson's model, which was the plum pudding model. It was like a failure, because actually the positive charge was not spread throughout the atom, but it was concentrated in a very small region. Then after that we did talk about the Rutherford's model, in which he did the experiment with the alpha ray. What are alpha particles consisting of? 2He4. They are the helium particles with a mass number of 4 and atomic number is 2. Then in Rutherford model, the major drawback was that he could not explain the stability. He could not explain the stability. Keep responding, okay? That will show me that you are awake. Then what we have is the order of the diameter is something like that you should know. The order of the diameter, you can even note it down somewhere. The order of the diameter of an atom is about 10 to the power minus 10 meters, and that of the nucleus is 10 to the power minus 15 meters. You can easily remember it also. And then we talked about the electromagnetic spectrum. And what do you have in the electromagnetic spectrum? I gave you a series of radiations which exist over a wide range of the wavelength. And what were those? X-rays, gamma rays, cosmic rays, X-rays, gamma rays, UV, visible, IR, microwaves and radio waves. And in this I told you depending upon how the electron is jumping from one level to another level, you will check out the difference between the two energy levels. When you check out the difference between the two energy levels, wherever that is falling, in whichever region it is falling, corresponding to that you will observe your spectra in that region only, right? After that we talked about the electromagnetic spectrum and we studied that what is spectroscopy. There is another branch of science that I introduced here at this stage. What is spectroscopy? It is the branch of science where you have the interaction of electromagnetic radiation with matter. Okay, and generally I am just telling you that whenever there is an interaction, there is always a change in the dipole moment. Generally that is considered as one of the important factors to observe the spectra. So whenever there is, like if this is matter and suddenly radiation falls on it, there will be some kind of an excitation of electrons or some kind of changes which will bring about changes in your molecules as well, right? Okay, then we came on to the quantum theory. In quantum theory what we basically have is that we talked about the Planck's theory, Planck's hypothesis, where he stated that you cannot simply walk through but you need to jump from one level. You as in, what am I talking about? An electron. It needs to jump from one level to another level. So you've understood the concept of quantum theory of radiation quite well. And there we had checked up some numericals. See, numericals in this particular topic are really very simple. You will have direct substitution of the values. You know your Planck's constant 6.626 into 10 to the power minus 34 joule second. We've revised it. Please repeat it again with me so that you all remember it from now on and forever. What is it? 6.626 into 10 to the power minus 34 joule second, and that multiplied by the frequency. What is your frequency? It is C upon lambda, where C is your speed of light, which is 3 into 10 to the power 8 meter per second, sorry. So then here if I talk about electron volts, then in electron volts I can calculate my energy as, I've just put it here, 1240 upon lambda in nanometers, and then your energy will be calculated in electron volts. This also is clear to everyone. You remember this value. What is your delta E equal to? It is equal to 1240 upon lambda. Remember that this lambda we are expecting it to be in nanometers to give your energy in electron volts. Then thereafter we also talked about the photoelectric effect. One important feature of the photoelectric effect is that although photoelectric effect was observed in 1880s also, but what was the photoelectric effect? The moment the radiation falls of a particular frequency which is greater than the threshold frequency onto the metal surface, what will come out of the metal surface? Electrons. So photoelectric effect refers to the ejection of electrons from the metal surface when light of certain radiation falls on it, and remember that this radiation should be having an energy which is greater than the threshold energy. Clear to everyone? There were four important postulates of photoelectric effect. One, that you need the threshold frequency or the threshold energy for the electrons to be ejected. Okay, then the second thing was that the kinetic energy of the ejected electrons depends upon the frequency. It depends upon the frequency and not the intensity as was believed earlier. This was like a deviation. Remember, kinetic energy was directly proportional to frequency. Repeat it again. Kinetic energy was directly proportional to frequency. Okay, and then the third point was talking about the number of electrons which are ejected. That depends upon the intensity. And fourth point I stated was that there should be no time lag between the incident radiation and the ejection of electrons. So there should be no time lag. And the important equation from which again numericals can be asked. So you can keep jotting down the formulae separately. One were the values which were important that we had just done, and the second thing that comes up are the formulae which are important from your numericals point of view. The theoretical concepts, as it is you are intelligent enough to understand them simultaneously, I am sure, to retain them forever. Now here what you have is that the total energy which is supplied is equal to the kinetic energy plus the wave function. This total energy according to Planck's theory is equal to h nu. It will be some kind of a packet of a quanta that we are talking about. So here we have h nu. What is your kinetic energy? Half mv square. So it has mass, it has velocity. So just in case if the question asks for velocity, you should it should immediately strike to your mind. This is the work function. Generally in many of the books it is represented as phi. Phi is the work function. So do not get confused when you see this phi. This phi is your work function which refers to h nu naught. It is equal to h nu naught, and from here only we got that kinetic energy is equal to total energy minus phi, that was equal to h into nu minus nu naught. Okay. Then we did talk about hydrogen spectra, because till that stage what was the problem with the atomic structure was that nobody could actually explain the spectra which was generally observed. So for the hydrogen spectra, first let us understand what is a hydrogen spectra. It is a kind of a line spectra. You remember the diagram that we had drawn last time, where all the radiations or the jumping of the electron was happening from the higher levels, from any of the levels to the ground level for Lyman, then from any level to n is equal to 2 for Balmer, then you had Paschen for 3, that is we are talking about the lowermost level, and the electrons could come from as far as infinity to that level and from any level. So delta n had no limitation here. For Brackett and Pfund and Humphrey series you can easily see. So this was the lower level was 1 here, 2, 3, 4, 5 and 6. Another thing here is that when I talk about the spectra, you know that this was observed in UV region. So this question is asked many a times in the entrance examinations. Last time I just taught and didn't tell you which all things are like, laid more emphasis on. Which is the level which is observed in visible region? Balmer. Alright. Which in UV? Lyman. All the rest of them are in the higher wavelength region, which is like IR, Paschen, Brackett, Pfund, Humphrey series. So I just wanted to have a look, you all to have a look at the hydrogen spectra. See, this is how it looks like. This is how it looks like. See, here you have kind of Lyman. What are these lines referring to? Let me tell you, this is some kind of a parameter where you can measure the wavelength. I told you that your spectra is always between the energy and the intensity. Remember, I'll just do it on the board for you. Last time I told you that you check up the transition from the different levels that you have. Say if this is n is equal to 1, sorry they are equally spaced, but otherwise they are not. I just drew them like that. So it is coming from infinity to 1, then from this level to the, so it comes like this, something like this, right? Now this energy difference, if it corresponds to a particular energy here on the spectra, you know how to draw a graph, all of you all, how to draw a graph. So whatever energy comes from this delta E, I mean from this transition, because if it goes from say E4 to E1, so what is your delta E in that case? E4 minus E1. Now this delta E will give you some energy that will have a particular intensity. If it is highly favored, just मान लो कि if it is very simple for the electron to jump from the 2 to the first level, so सबसे ज़्यादा intensity किसकी होगी? उसी level की जिसके chances ज़्यादा हैं to get pumped up from one level to another level. You getting the point? So that will show the higher intensity peak. Now here in this case, this delta E is first calculated and then we plot this delta E versus intensity. This graph where we actually keep plotting, say now supposedly it falls at x nanometers. So here I will just put x nanometers and I will get a peak here. Okay, the x axis corresponds to your energy values. Say this is like x1. I get delta E as x1. That x1 will be plotted and that will give you a peak in your spectra. Then maybe the next transition may be say x1 plus 10 nanometers say. So then in that case it will be plotted somewhere here. So that way you will get a series of line for Lyman, then a series of line for Balmer. Now this energy region will be falling in your say UV, then you will be actually plotting it accordingly. So this is the spectra which is obtained from the calculations or the jumping of the electrons from different levels accordingly. So this is the kind of spectra as to how it looks like. You've done it theoretically, but when it is actually checked experimentally, this is how it looks like. Like for example, now you can get it. If this is representing your Lyman, this is your Balmer because it is in the visible region. So now you know that here what is your n equal to the lower one? 2. Speak it up, be confident. You know that n will be equal to 2. So that means the value of energy required in jumping from a higher level to a lower level would be all lying in the visible region like this. This is only just to show you. Nobody is going to ask you to plot a graph. But you should know that this is like the visible region. And then thereafter you have the rest of the series in your IR region. So you get that somewhat? Yes? See here, first look at the spectra. You want me to explain the spectra again? So here if you look at the when you look at the spectra, this is the graph that I had drawn on the board. You have the energy values. Okay, these energy values, like the first one, maybe it is at a lower wavelength, means it is at a higher energy. Maybe that lower wavelength means higher energy, right? E is equal to hc by lambda. They are inversely proportional. So you will have, if the wavelength is small, then the energy will be large. Now if the wavelength here is small, that means that transition is happening from a higher level to a lower level such that the energy gap is more and the wavelength is small. So when we plot it for wavelength, we know that it is corresponding to this particular wavelength. And what graph that I drawn here is between not the wavelength but energy. It is not the wavelength but the energy. So accordingly, wherever your transition happens, depending upon where this delta E falls, if this energy falls in the UV region, you will observe your peak in the UV region only. If this energy difference corresponds to your visible region, you will be observing the energy lines in the visible region only. What you will get is, you will get the data for delta E. Okay, then if you are plotting the graph simultaneously, you will note that delta E and make a line at wherever that delta E is. That is how this graph is plotted. This is only for your interest to develop, that this is how it looks like and this is what had to be unfolded as to how do we actually obtain it. Then thereafter we actually checked up for this Lyman-Balmer series that your wave number, what is your wave number? 1 upon lambda, and wave number is represented by nu and there is a bar on top of it. So nu bar is equal to 1 by lambda and it is equal to r z square into 1 by n square minus 1 by m square, where n and m are the two levels between which the transition is happening. This r value 10, I want all of you all to speak up. It is 109677 in centimeter inverse. This is very important because your wave number is 1 upon lambda. Lambda is in meter or centimeter, so the units will be of that of meter inverse or centimeter inverse. This R value of 109677 is in centimeter inverse, and this Z square is your charge. And remember, this is another formula from where you can get questions from this particular topic. So again, simple, all the values will be given to you. You just have to substitute and get the answers. We'll take up questions as we proceed. Then we came on to the Bohr's model. Bohr, in fact, was a student of Rutherford. Okay, so one gets inspired by the teachers under whom you take a training. So Rutherford did his experiment and it had a major drawback, that it couldn't explain the stability. So then Bohr took it up and he introduced some newer concepts. We have talked about Bohr model also. What newer concepts did he introduce? He says that there is a fixed orbit. Okay, he talks about a fixed orbit. You have the nucleus in the middle and you have fixed orbit. Another, how will you actually talk about the concept of fixed orbit? That is talked about when we talk about the angular momentum of the electron. What did he have to explain? Why is not the electron coming to the nucleus? Why is it not collapsing with the nucleus? So there he explained that the angular momentum is quantized. क्वांटाइज्ड का क्या मतलब है कि मैंने आपको एक पैकेट दे दिया, then you have to actually, if you have to actually now distribute, either you have to take up another packet to distribute or else you cannot divide that packet. So angular momentum also, he gave that a particular value of h upon 2 pi, and he says that that value will always correspond to a multiple integral multiple of this. What is your angular momentum? mvr. That factor is h upon 2 pi, and total expression given by Bohr was that your angular momentum is quantized, means that it will be some integral multiple of h upon 2 pi. So now supposedly if I want to find out what should be the angular momentum of the electron in orbit number 1, it will mean that n is equal to 1. What is the orbital angular momentum of the electron when n is equal to 2? Simply your n will be equal to, for the second level, their n will be equal to 2. So you know that mvr will then remain constant for a particular orbit, and it will keep on moving like this, like you have the earth revolving around the sun. It's just a revolution that it will take. This is what Bohr postulated. Then thereafter you have the velocity expression, which is very important. I gave you all these expressions last time. So I hope you can just recall them right now and memorize if you have not done it. It will take about 2-3 seconds only. Velocity is equal to 2.18. Once again, 2.18 into 10 to the power 6 z by n. Z in meter per second, its velocity. Z is your charge, n is the level which you are talking about. Okay, and then you have the radius. Radius is equal to 0.529 into n square by z. If you say 0.529 n square upon z, then I am talking about it in angstrom. So remember this 0.529 factor also. And just tell me what will be the radius for the first orbit of hydrogen atom. Angstrom. Please say that. What will it be? Rn will be equal to 0.529 angstrom. Okay. Remember this, that here the radius will be 0. So this is known as the Bohr's radius. That corresponds to n is equal to 1. It's the first orbit of the hydrogen atom. So the very first one corresponds to an energy of 0.529 angstrom. And no, 0.529 into 10 to the power minus 10 meters. I haven't put it here, that will be meters. And I am saying if I remove this 10 to the power minus 10, you know it's angstrom in meters, right? Angstrom meters. So that will be, now En will be equal to the energy that we had done in joules per atom, in kilojoules per mole, and in electron volt. Let me tell you, all these three values are very important for you, for all those of you who want to crack the IIT exam. Okay? Remember that these three values are important, and whenever you get up in the morning, you should carry only one thing for the next 2 years almost, that we have to clear the IIT. Don't just tell yourself, see yourself placed in IIT, and only then it will inspire you to study more. Okay, so then you have one value which is minus 2.18 into 10 power minus 18 z square upon n square. Another one is minus 13.6 z square upon n square, that's in electron volts. And then you have in kilojoules per mole, that is minus 1312. Again z square upon n square factor remains the same in kilojoules per mole. I hope you remember how did we get it from joules per atom to kilojoules per mole. We multiplied it with your 6.022 into 10 power 23. Okay, and that is because I have done mole concept with you, so I expect you all to remember that particular magical number. What is that? 6.022 into 10 power 22. That's the base of chemistry, so you shouldn't be forgetting the first number which you were supposed to memorize. Then frequency. There was a numerical that we had done based on it. So numericals of this type can also be asked, where a little twist is that you are given, say you were given the total distance covered. How will the electron move? It will move in a circular pathway. And what is the circumference of a circle? 2 pi r. So generally the total distance covered by an electron will be in terms of 2 pi r only upon velocity. velocity will be the speed that will be given in a particular direction. So there the velocity will also be mentioned. What is your total distance upon velocity? That gives you the time. Simple concept. And what is inverse of time period? That is your frequency. If you know the frequency, you can calculate the energy. What is your energy? It is h nu. Your energy is h nu. So once you know nu, then you can calculate energy. So